As we look at section 2.5, we're going to move away from linear and look at some absolute value equations and inequalities. And so when we look at an absolute value, we can look at it in a table. Absolute value of -2 is 2, -1 is 1, 0 is 0, 1 is 1, 2 is 2. So we get this XY chart, which would yield this graph. And so one of the things that we start to notice and remember about absolute value graphs is they're always in the shape of a V. If you do not have a V, you do not have your absolute value graphed properly. The domain would be all real numbers because it goes forever and ever from left to right, but the range would only be values from 0, including 0, up to infinity. So here's your domain is all real numbers, range is everything greater than or equal to 0. We increasing from 0 to infinity and decreasing from negative infinity up to 0. So we have all of those things as our basics. One of the ways that you can also define an absolute value is to use a piecewise function. The absolute value of x is the opposite of x if our x is negative, or exactly x if our x is greater than or equal to 0. But that's what an absolute value does, right? It changes the sign to a positive if you start out negative, and it leaves everything alone if you're 0 or positive. Another formula that they use for it sometimes is that the absolute value is the square root of x squared, because when you're given the square root symbol, that's always the principal square root, and the principal square root is always non-negative, which means the smallest it could be is also 0, which is the same idea as an absolute value. All right, so for the function here, which is f of x equals the absolute value of x plus 1 minus 2, they ask us to identify all x and y intercepts. So our x-intercepts, there should be, in this case, 2 of them. So something comma 0 and something comma 0. As we come in here and look at these, it's going to intercept here and intercept here. So our values are -3, 0 and +1, 0. And if you check the math on that, if we plug in -3 plus 1 is -2, whose absolute value is 2, 2 minus 2 is 0, so that works. And if we plug in 1, 1 plus 1 is 2, whose absolute value is 2, 2 minus 2 is 0. So all of that checks out perfectly. And then if we look at our y-intercept, here is the y-intercept on this graph. So that's going to be over 0 and down 1. So 0, -1. And again, if we check that, that means we're plugging in 0 for the x. 0 plus 1 is 1, whose absolute value is 1. 1 minus 2 is -1. That is the output that we got here. So that checks out. In part B, they ask us for what x values is f of x greater than 0, f of x less than 0, f of x equal to 0. Well, the f of x equal to 0, you've actually already answered, because what this says is y equals 0, and we found 2 places where that happened, -3 and +1. So we would put those inside of a set because those are just a list of numbers. There's 2 places where it happens. -2 and +1 are the 2 distinct places where that, -3 and +1 are the 2 distinct places where that happens. Now, as far as where is it less than 0, so our less than 0 on the graph would be this stuff here. So the x interval would go right in here, right? It starts at that -3 value and stops at that +1 value. So our less than 0 would be interval notation starting at -3 and stopping at 1. Then for our greater than 0, they cut off the graph here, but it continues to go up here, and it's up here. So as far as the x interval, it would start here and go this way. It would start here and go this way. So our interval notation would start at -infinity and stop at -3, unioned with, it would start at 1 and run out to infinity. So it's greater than 0 on these two pieces. It's less than 0 in the middle, and it's exactly equal to 0 at those two specific x values. All right, where is your function increasing? Where is your function decreasing? So increasing and decreasing. The increasing starts at this turning point and goes this way. So the x values start here and go this way. So we're talking about everything from -1 to infinity. Decreasing is everything over here. So our x interval would stop here and include everything to the left of that. So that would be everything from -infinity to -1. And that takes care of increasing and decreasing. And then they ask us finally to give the domain and the range. The domain of every absolute value graph is all real numbers, so we have -infinity to +infinity as our domain. The range can change as we move the graph up and down, and we see that here. The lowest we touch is right here. So our y values go like this on the number line. So that means we start at -2 and run up to infinity. Start at -2 and run up to infinity for our range value. Oh, I put a parenthesis on that though, but wait a minute. We do actually touch -2, right? There's a closed circle there, so it should be a square bracket. There we go. We do touch -2, so it should be a square bracket on that -2 value and then run up to infinity because we do actually touch -2. One of the ways we sometimes teach to graph absolute values deals with a partial reflection of whatever's the inside of the absolute values. So that's kind of what they're looking at here. So what we're going to graph in this first spot is y equals x plus 2, which would be a slope of 1 and an intercept of 0, 2, right? So if we look at that, here's our 0, 2, here's our slope of 1, and we're drawing a straight line. Through those values. Then over here, what they want us to graph is y equals the absolute value of x plus 2. So the values that were positive, this goes back to the idea of this piecewise definition here. The values that were already positive are going to stay positive, and the values that were negative we need to reflect. So the values that were already positive were these guys right here. So they're going to stay exactly the same as we bring them over here. So it went through at -2, intercept on the y-axis at +2. So this part of the graph is completely unchanged. Now the part that needs to change is this part of the graph. So what used to be negative, if my output was -1, when I put it in absolute values, now it's going to be +1. If my output was -2, when I put it in absolute values, now it's going to be +2. If my output was -3, my output in absolute values would be +3. -3 changes to +3. So now we're looking at this part of the graph being reflected, is what we're looking at, up over here into the positive values, and that gives us our V-shaped graph. Okay, so we took the values that were negative over here and reflected them because their absolute values would be positive in that second graph. All right, for this one, same idea here. We're going to graph y equals -2x plus 4. So that's going to be a slope of -2 and an intercept of 0, 4. So 1, 2, 3, 4. We're going to go down 2 and right 1, down 2 and right 1, down 2 and right 1, up 2 and left 1, up 2 and left 1. All right, so our graph would look like this. Now, when we talk about graphing, y equals the absolute value of negative 2x plus 4. Again, these parts that were already positive stay exactly where they were. So that was crossing through at positive 2. So this part of the graph is unchanged from what we had in the first graph. The part that will need to be reflected is this portion over here. So it's going to go from a y value of negative 2 to positive 2, of negative 4 to positive 4, of negative 6 to positive 6, and so on, so that we see our V shape coming in there by using that reflection. Now for linears, that's pretty easy to visualize. The more complicated the graph, the more complicated that can be because you have different areas that you have to look at. So here's a linear. This is like what we just did there. Then they look at another absolute value of a parabola. So this part is what would need to be reflected, this red region here in the middle. And so when we flip it up into the positive, it sort of creates almost like a W graph when you do that instead of your U-shaped parabola graph that you expect to see for x squared. In the title of the section, it says we're going to look at equations and inequalities. So we start with equations. So the visual concept of solving absolute value of ax plus b equals k. So you know that the blue, your V-shaped graph, is your absolute value of ax plus b. It's always going to be a V-shaped graph. Then there are three options for that constant. Either it's a positive constant and it runs through and touches the graph twice, or if that constant is 0, it touches the graph exactly at the turning point, or if that constant is negative, it never touches the graph. So there are three things that can happen. The most common is this one, where we have two solutions because it crosses through that V-shaped graph twice. If you're exactly at the turning point, you'll have one solution, and if you're negative, you'll have no solutions. So how do we solve those algebraically? Well, when you are given something that says the absolute value of ax plus b equals k, you create two separate equations. One of them says ax plus b equals positive k. The other says ax plus b equals negative k. And then you solve those two equations independently. So for example, in part A, they tell us the absolute value of 3/4 of x minus 6 equals 15. As soon as I see it's an absolute value set equal to a constant, it creates two equations, 3/4 of x minus 6 equals 15, or 3/4 of x minus 6 equals negative 15. One of those two, and both of those are going to be solutions. All right, so as we look at that, we're going to add the 6 to both sides to get rid of the 6's. So that's going to say 3/4 of x equals 21 here. 3/4 of x equals negative 9 here. Then to get rid of the 3/4, I'm going to multiply both sides by 4/3. So that would just leave x equals, it'd be 7 times 4, which is 28 for one of my solutions. X equals, it would be negative 3 times 4, so negative 12 for my second solution. So we have two solutions. We have x equals 28 and x equals negative 12. Back to our graphical explanation that we had up at the top of the page. If we go to a graphing calculator and we put into y equals the absolute values of 3/4 x minus 6, which was our left side, and y equals 15, which was our right side, the red graph is our absolute value, the blue graph is our y equals 15. And sure enough, we see 2 points of intersection. This one would be at x equals negative 12, and this one would be at x equals 28, which does verify the two results that we got very quickly, giving us a quick visual verification of our solution. Okay, then in part B, they're telling us that the absolute value of 1 minus 2x equals negative 3. So it says an absolute value equals a negative number. This is a false statement. It can never happen. This has no solution. Absolute values, by definition, cannot be negative, right? So this has no solution because it's an absolute value set equal to a negative number. That's the problem with it. We get a graphing calculator to help us with a quick visual confirmation of that result. Here I have the red is y equals the absolute value of 1 minus 2x, which was our left-hand side, and the blue is y equals negative 3. So you see the V graph and the blue graph never touch each other, right? If they never touch each other, that means there's no solution. So we can be confident in our answer to part B. C says the absolute value of 3 minus 2x minus 5 equals negative 2. Now, be careful. Yes, it says right now it equals a negative number, but we don't have our absolute value isolated. And that needs to be the first thing that we do is isolate the absolute value. Okay, that needs to be our first job. So what that means is we're going to add 5 to both sides. So when we get done with that, it says the absolute value of 3 minus 2x equals positive 3. So now we have an absolute value equal to a positive number. We can proceed with the solve because equal to a positive number works just fine. So that's going to give me two equations to solve. The first one says 3 minus 2x equals 3. The second one says 3 minus 2x equals negative 3. All right, so we would subtract 3 from both sides, which would say negative 2x equals 0. Negative 2x equals negative 6. Divide both sides by negative 2. X equals 0 is one of our solutions. X equals positive 3 is our second solution. So we end up with two solutions. They are x equals 0 and x equals positive 3. I totally wrote the problem down wrong. Oh. Our answers are right for what we had. Let's just change it. That'll be maybe easier. Absolute value of, I wrote down 3 minus 2x minus 5 equals negative 2. Those are the solutions that we get for that since I copied the problem down wrong. Let's verify those results graphically. Solved said the absolute value of 3 minus 2x minus 5 was my left-hand side and negative 2 was my right-hand side. So we see our red V for the absolute value, our blue at negative 2. We see 2 points of intersection. This one would be at x equals 0, and this one would be at x equals 3. That does correspond to the two solutions that we got. What it was supposed to be, but the problem written down right. Let's try again. I'm going to now call this part D. The original part C said the absolute value of 3x minus 2 minus 5 equals negative 2. Never hurts us to have an extra example. So again, we would need to isolate that absolute value first. Our goal is to get the absolute value by itself, which means we're going to add 5 to both sides, which would say the absolute value of 3x minus 2 equals positive 3. That we can solve. It gives us two equations, 3x minus 2 equals positive 3, or 3x minus 2 equals negative 3. So then we can add 2 to both sides, which would say 3x equals 5 and 3x equals negative 1. Then we're going to divide by 3 to get x equals 5/3 for one solution, and x equals negative 1/3 for the second solution. So still getting two solutions. This time my two solutions are fractions. That's fine. 5/3 is one of my solutions and negative 1/3 is the other solution. Verify those results graphically. Here I've put in y equals the absolute value of 3x minus 2, then minus 5, and y equals negative 2. We see our red V for the absolute value, our blue line at negative 2, and we see 2 points of intersection. this would be at -1/3, and this would be at -5/3 in fraction form. Of course, your homework is going to want it in fraction form, so we do verify those results using our graphing tool. Example 4, they're looking at a word problem here. It says the maximum and minimum diameter d in inches of a cylindrical can satisfy the equation the absolute value of x minus 3 equals 0.02. Find the maximum and minimum acceptable values. So really, they're just asking us to solve this. Now, later at the end of this section, they're going to talk about an application that is the tolerance of error. That's really what this is an example of. They're saying they want 3 inches to be the diameter, but we can allow an error of up to 0.02 inches. So everything that falls within that will be acceptable. Everything outside of that will have to be thrown out. So our equations to solve would be x minus 3 equals negative 0.02. X minus 3 equals positive 0.02. So we add the 3 to both sides, and we get x equals positive 2.98 would be the smallest acceptable diameter, and x equals 3.02 would be the largest acceptable diameter. Those were both being measured in inches as far as that goes. So the smallest would be 2.98, the largest would be 3.02. Then, for the first time, we have two absolute values set equal to each other. And in a lot of ways, it solves exactly like the number 4 example or any of these that we've done so far. You want to think of one side being sort of like your constant, and then the other side is like your absolute value. So what we're going to say here is x minus 2 equals something, and x minus 2 equals something. We're going to create two equations. For one of those equations, we're not going to change anything. 1 minus 2x stays exactly like it was. For the other equation, we're going to talk about the opposite of 1 minus 2x. Now, most common mistake to make on these is in this equation where you've changed one side, you change both. Don't change both. One of your sides, in my case, I chose the left side, that x minus 2, he has to stay the same in both equations. X minus 2 has to be in both. Then you have the right side left alone and the opposite of the right side. That's how you generate your two equations. All right, so then we solve these two things independently. So here we could add 2x to both sides and add 2 to both sides. So that would put me at 3x equals 3. Divide both sides by 3, and we get x equals 1 as one of our solutions. Over here, we would need to distribute first, so x minus 2 equals negative 1 plus 2x. Then we could subtract x from both sides and add 1 to both sides, which would say negative 1 equals 1x, which would be our solve, right? Negative 1 equals x, and we've got it. So we've got solutions of negative 1 and positive 1. So again, if we want to try to show this graphically, we can go to our graphing tool. Y equals the absolute value of x minus 2 was my left side. Y equals the absolute value of 1 minus 2x was my right side. So in red, we have the x minus 2's absolute value. In blue, we have the 1 minus 2x absolute value. We see there are 2 points of intersection. Those 2 points of intersection have x equals negative 1 and x equals positive 1 as our two solutions. And indicated that we were going to look at inequalities also. We have not done that yet. Here's where we're going to start doing that. So they're looking at the absolute value of ax plus b is less than k, or the absolute value of ax plus b is greater than k. So our k value is this red line. Our absolute value is this blue v. So the blue V dips below the red line in the middle. So it's going to have one region right there in the middle of whatever these 2 points of intersection were. The blue is above on the two tails. So you're going to have two regions of solutions based on where these points of intersection were. It's going to be everything to the right and everything to the left left of the negative, right of the positive as we're looking at that. So less thans are in the middle, less thans are in the middle, less thans are in the middle. So when we're talking about the absolute value of ax plus b is less than k, you have negative k and positive k, and you put the ax plus b in the middle. Less thans are in the middle. Greater thans give us the two tails. So the less than is the negative k, the greater than is the positive k. We want to be less than on the left, which is the negative values, greater than on the right, which is the positive value. So less than negative k or greater than positive k. So if we look at some examples of how this plays out, as soon as we see it's a less than, what goes through my head is that means it's the region in the middle. So we're going to say negative 4 is less than 4 minus 2x is less than positive 4. We're putting the 4 minus 2x in the middle of negative 4 and positive 4 as we look at that. And then we solve that compound inequality. So in this case, we would subtract 4 from all three places, which would put me at negative 8 is less than negative 2x is less than 0. Then we divide by negative 2, which means we have to remember to flip around the inequalities. So we'd have positive 4 is greater than x is greater than 0. So 0 to 4, open and open. In the middle, everything from 0 to 4 would be our interval notation. Everything from 0 to 4 is what belongs in our interval notation. Then, if we see this greater than, when I see a greater than, I'm thinking about two tails is what I think of in my head, the left tail and the right tail. So the left tail says the 4 minus 2x is less than negative 4, or the right tail says 4 minus 2x is greater than positive 4. You have to, one way you can help yourself remember this is if you're switching from 4 to negative 4, you multiply it by a negative 1, right? Which is why we have to flip that inequality around and change it from greater than to a less than. If you want left, it has to go left. The only way you can go left is a less than, right? So however you can get that squared away in your head. All right, so then we solve these two things independently also. So we're going to subtract 4. So that puts me at negative 2x is less than negative 8. This puts me at negative 2x is greater than 0. Divide by negative 2. Remember to flip. Divide by negative 2. Remember to flip. So this now says x is greater than positive 4 or x is less than 0. So on a number line, we have 0 and positive 4. Greater than 4 would shade over here. Less than 0 would shade over here. So it's everything from negative infinity to 0, union with everything from 4 to infinity. So this would be our solution set. I wanted to take a graphical look at that. Here we have gone to the graphing utility. My left side was the absolute value of 4 minus 2x, and then my right side was positive 4. So if we wanted to know where they were exactly equal, if we wanted to know where does the absolute value of 4 minus 2x equal positive 4, we would get x equals 0 and x equals 4. We see these 2 points of intersection here, x equals 0 and x equals 4. Now, if we want to know when is the absolute value of 4 minus 2x less than 4, that's going to be in this part right here. That's where we drop down below the 4 line. So as far as our x-axis answers go, we're going to start at 0 and stop at 4, and we're talking about that region that's right in there. So our answer would be everything from 0 to 4. If we want to know where our absolute value of 4 minus 2x is greater than 4, well, that would be over here, it's above the 4 line, and over here, it's above the 4 line. So that's 0 and to the left, 4, and to the right. So that would be everything from negative infinity to 0, unioned with everything from 4 to infinity. So we can see that graphically. If we're going to be greater than 4, we would be above the blue 4 line. If we're going to be less than 4, we would need to be below the blue 4 line. And we can see how that ties together into those intervals graphically pretty quickly with a graphing utility. As soon as I see it's a less than, I'm thinking about in the middle. So we're taking our 2x minus 5 and putting it in the middle of, keeping the or equal to, since the original problem had the or equal to, negative 6 and positive 6. Make sure you put the negative 6 on the left because negative 6 is smaller than positive 6. Right, then we add 5. Good grief. We add 5 all the way around, which would put us at negative 1 is less than or equal to 2x is less than or equal to 11. And then we divide by 2, which does not require any flips. So negative 1/2 is less than or equal to x is less than or equal to 11 halves. So we would start at negative 1/2 and stop at 11 halves for our interval notation solution there. My left side was the absolute value of 2x minus 5. My right side was 6, and we were wanting to solve the absolute value of 2x minus 5 is less than or equal to 6. So the absolute value is less than, would be this region where it drops below. So we can see that that starts at this negative 1/2 value. And 5.5 is the same as positive 11 halves, which is what we had. And so we're going to be talking about on the number line, starting at negative 1/2, actually with a square bracket, we did have the or equal to, and going to 5.5, which is here. So this region is where we were below. So everything from negative 1/2 to positive 11 halves would be our region for our solution. As soon as I see it's a greater than, I'm thinking about 2 tails is again how I remember it. So for the left side, we need x minus 5 is less than negative 3. And for the right side, we need x minus 5 is greater than positive 3. And if you get that right, it's pretty easy solve. We add 5. So we have x is less than 2, x is greater than 8. So it would be everything from negative infinity to 2, unioned with everything from 8 to infinity for our solution set there. Back of that, we clearly are talking about where we went, where the absolute value of x minus 5 was greater than 3. So the greater than 3 is where we're above the blue 3 line, which is this left side and right side as shaded. So we're starting, this one is x equals 2. This one is x equals 8 for the point of intersection. So 2 and over to the left, and 8 and over to the right. So we do see that same solution set of everything from negative infinity to 2 unioned with 8 to infinity for our solution set there, which verifies the results that we had algebraically. Earlier, they're going to talk about the error tolerances as their big application here in this section. The value A must be located between S minus E and S plus E if E is that error tolerance. So in that example with the cylindrical can, our error tolerance was 200ths of an inch. And so we had to be between S minus 0.02 and S plus 0.02 as we looked at that. So if we turn that into an equation, the actual minus the specified must be smaller than the error. The difference between what we actually have and what the specs say we should have has to be less than that tolerance of error. So it says the iPhone 6 is 5.44 inches high. So our S value is 5.44 inches. Suppose that the actual A of any particular iPhone has a maximum error tolerance of 0.005 inches, so 5/1000ths of an inch. Write the absolute value statement that describes that. So our answer to part A would be the actual size minus the specified 5.44 has to be less than 0.005. And it does say less than, so we do not have an or equal to on that. It just says less than. Then in part B, they ask us to solve that inequality. So less thans are in the middle. So we're going to say negative 0.005 has to be less than a minus 5.44 has to be less than 0.005. So we add the 5.44 all the way around, which would put me at 5.435 is less than a is less than 5.445. So the smallest acceptable is 5.435 inches, and the largest acceptable is 5.445. And I guess actually that's not quite technically true because they don't have the or equal to's on there. Must be, instead of is, let's say less than, greater than. And less than here. An easier way probably to streamline it would be the actual is between. And if you put between in there, you get away with that not having no or equal to 5.435 inches and 5.445 inches as we're looking at that. So it needs to be bigger than 5.435, smaller than 5.445 to be acceptable. Anything other than that's going to get tossed into the junk pile and recycled.